So in the previous video, I introduced this idea of this frictional force providing the kind of central attraction that allows things to move in a circular path. And what I mentioned was that if the frictional force isn't sufficient, then this object will kind of slide off. Okay, so for a car, if you go around a corner where there's ice and the friction isn't sufficient, then there isn't enough force attracting you towards the center of the kind of circular arc that you're on, and therefore the car will slide outwards. So here's an example where we're applying that knowledge. It says a cat dozes on a stationary merry-go-round at a radius of 5.4 meters from the center. The operator turns on the ride at a rate of 1 rotation every 6 seconds. What is the minimum coefficient of static friction between the cat and merry-go-round that will allow the cat to stay put, i.e. not slide? So if we assume that the cat is not sliding, so let's assume that the cat is stationary, and that's stationary with respect to the merry-go-round, so it's not sliding. That means then that it is executing this uniform circular motion. So essentially then it's just moving around in a circle in line with the rotating merry-go-round. Okay, so it's not sliding to a different position on the rotating disc. So the speed of that rotation is going to be given by well, what's the linear distance traveled in a circle? It's so the angle that we sweep out if we do a full circle is 2 pi radians. And so the distance that is traveled is 2 pi times the radius. So that's the linear distance traveled. And then the time that's taken to do that rotation is the time period t. And so our velocity, or sorry, the speed of that rotation is 2 pi times 5.4. That's the radius that's given to us in the question. Okay, that's a radius of 5.4 meters. And the time is also given to us. We do 1 complete rotation in 6 seconds. Okay, so we just plug in those numbers and we get a rotation, a speed of 5.65 meters per second. That's our linear speed. So the acceleration then, well, the acceleration is just v squared over r. So that's going to be this 5.65 squared divided by the radius, which is 5.4. And if we plug those numbers in, then we get an acceleration of 5.91 meters per second squared. So that's our acceleration for a cat which is going around in a circle like that. Now then we can calculate what the forces need to be. So Newton's second law tells us that the net force is equal to the mass times acceleration. Well, the only force which is acting kind of in the plane of this motion is the frictional force, which is attracting the cat towards the center. So our net force will be the frictional force, which is our static frictional force. So it's our FF, our frictional force, and that frictional force will be less than or equal to the maximum frictional force that could be applied. Okay, so if we're right at the limit where the cat is about to start sliding, then this is the force that's acting to stop it sliding. If we're not quite at that limit yet, then we have some other force which is going to be less than or equal to that value. And that frictional force is given by the coefficient of static friction multiplied by the normal force. And if you think about the cat, I'm not going to attempt to draw a cat sitting on this merry-go-round. The two forces that are acting in this direction then are its weight, mg here, and the normal force. So because it's not floating off into space or sinking into the disk, these two things must be equal. So we have that mu s times n is the same thing as mu s times mg. Okay, so that's the net force. That then will be equal to, so this whole thing, mu s mg, must be equal to the mass times the acceleration. And we've just written down the acceleration here, so that's equal to mass times 5.91. So the mass here cancels out on both sides, and we're left with mu s. Sorry, it's difficult to write at the bottom of my iPad, so let's try that again. That leaves us with mu s is equal to 5.91 divided by g, which is 0.6. So that is, and there's no units for that. This coefficient of static friction is a ratio of two forces. and therefore the units cancel out. So the coefficient of static friction that we need for this then is 0.6. And that then, as long as we have a minimum coefficient of 0.6, that means that this force is sufficient to stop the cap sliding outwards. In other words, the force is sufficient to maintain this acceleration.